Okay, I think we can start the second talk of this afternoon, the second and last talk of this afternoon session. The speaker is Nadezhda Ribarska from the University of Sofia, and she will talk on non-smooth problems of calculus of variation. Please.
Thank you very much. And thank you very much to the organizers for this opportunity to speak in front of so pleasant and audience and share some experience. So I have to share my screen with you.
Yes.
Yes. And here is this presentation. I'll try to make it full screen. Maybe. Okay.
That's okay.
That's okay. Okay, it doesn't work, but that's okay, maybe. Yeah, so the topic of my talk is on a non-smooth problem of the calculus of variations. And as a matter of fact, it's a long project. And I'm going to speak about some results with Mikhail Krastanov and some other some of our students obtained for the last 3 years, for example. Of course, okay, what's the problem? Okay. Of course, the calculus of variation is too celebrated and long-lived field in mathematics. Is the oldest branch of optimizations. I think the problem of brachistochrone, which is considered as the very beginning of this branch, is 300 and something years old. So, and it is the ancestor of the field of the optimal control. But we want to speak about, I want to speak about non-smooth versions of the basic problem of calculus of variations, and to speak about it from a point of view of the functional analysis, because the development of functional analysis made it possible to consider this problem as a constraint optimization problem in an infinite dimensional space. And it began since 1965. Dubovitsky, Milutin should be considered as the ancestors of this approach. And during these years, it is a spiral, you know. Sometimes people prefer to think about this problem from an infinite dimensional point of view, and sometimes people prefer to have the local point of view, point-wise. And for last decades, maybe 2 decades, the local approach is prevailing, and it's our conviction that it's time to go back and to look at it again from an infinite dimensional point of view. Okay, let us remind the basic problem of the calculus of variation, the simplest but non-trivial formulations. So you have some integrand L, which depends on the time, on the space variable, and on the velocity. And you want the integral functional, where x is an absolutely continuous curve, so x dot is well defined. You want to minimize this integral functional, subject to the restrictions that the beginning of the curve and the end of the curve are fixed points in Rn. Sure, one has to specify some, to impose some conditions on the integral in order, on the integrand in order this problem to be meaningful. It is classic. It is classic to when L is smooth, then the necessary condition is the famous Euler-Lagrange equation, and it need not be advertised. It's famous enough. We are interested in obtaining necessary conditions in non-smooth and, if possible, non-Lipschitz setting. Non-Lipschitz, the integrand to be non-Lipschitz with respect to the first variable. So if you want to attack this problem from an infinite dimensional point of view, that is to obtain a necessary optimality condition for the basic problem of calculus of variations, one should find a Lagrange multiplier that is a non-trivial linear functional separating the tangent cones to the epigraph of the integral functional and to the constraint, respectively, to prove regularity of the obtained Lagrange multiplier and to find reasonable conditions connecting the Lagrange multiplier with some selections of normals to the epigraph of the integrand. It's too general to be meaningful. So in this next slide, I'll explain a bit more. But now I want to say that in this talk we present some results connected to the first item here. We have some works concerning the second and the third, but now you want to concentrate to the possibility to find a Lagrange multiplier. And because it's very non-smooth, one should approximate in a reasonable way the epigraph of the function. But first, let me show a more precise formulation of the problem. So by X, we'll denote the Banach space L infinity. Functions defined on the interval AB and values in Rn. And let Y be L1. Of course, L infinity is the dual of L1. And unfortunately, the dual of L infinity looks awful. So this was the reason to have in the previous slide, one should prove regularity of the obtained Lagrange multiplier, because if you say that you obtained a functional belonging to the conjugate of L infinity, all optimal control people will kill you. So it's not reasonable to do it. You should find a regular Lagrange multiplier. So you have the integrand for the time being, let it be continuous. We'll have more restrictions on it. Continuous with respect to the first variables in Rn and Rn. These are the state variable and the velocity, and it is measurable with respect to the last variable, its time. And of course, we are not sure a priori that x ut are L of x ut is a summable function, but it is, if it is not summable, we just say that the value of the integral function is plus infinity. So we have a function defined on x times y, and the values are in extended real line, the real line plus the symbol plus infinity. What's the constraint? The constraint, we want the x, the first variable, to be an absolutely continuous curve. And u to be its x dot. So we can write beginning from xa and ending at xb. So this is the constraint, and you can see that the constraint is very simple, very simple. It's an affine subspace of x times y, so it does not present any difficulties when you want to approximate it, and so on and so on. The main difficulties, are concentrated in the epigraph of the integral function. So in this setting, the basic problem of the calculus of variation is in fact find the minimum of this integral functional when xu belongs to S. So now we want to find a Lagrange multiplier. That is, if x bar, u bar or y bar, sorry for this, is the solution of this problem, at the minimum point, you want to find a functional which separates the set S times minus infinity, the value at the solution, and the epigraph. If I can try to, this is I'm sorry. So you have some epigraph of your functional, you have some constraint, and here, if it is the minimum, on the constraint you have something like this, and you put here the constraint minus infinity. Okay, I couldn't draw it very well, but maybe the idea is clear enough. So we have to find good approximation of the epigraph. This set, it's clear was the approximation. To find hyperplane which separates the approximations in order to obtain the Lagrange multiplier. But it's not enough. It's not enough, I mean, to find a hyperplane which separates the approximations. We have to show that if the approximations cannot be separated by a hyperplane, that the sets cannot be separated, which would be a contradiction to the fact that we are at a minimum point. This we call a non-separation result. So this is the the precise definitions. So if we have two sets A and B with a point x dot x0 at their intersection, they are said to be locally separated at x0 if there exists a neighborhood of this point such that at this neighborhood there are no other points in the intersection except for x0. Of course, just like this, if the minimum is not a strict minimum, it's not the case, but it's always possible to have a little perturbation in order to make the minimum point a strict minimum point. And then at the solution, the epigraph and the set, the constraint times minus infinity, the value minimum, these two sets are locally separated at a local minimum, local strict minimum. So non-separation result is not always true. Is not always true, and it somehow is related to the idea of transversality. Of course, transversality of now I am going to say something which everybody knows from his or her first year in the university when learning about Lagrange multipliers in a smooth setting, and there the teacher talks about independence of the constraints. So in differential geometry, if you have two smooth manifolds and a point in their intersection, it is said that these manifolds are transversal at this point if the sum of the corresponding tangent spaces is the whole space. And it's an observation, pretty easy, that if you have two smooth manifolds which are transversal at some point, then if the corresponding tangent spaces have non-trivial intersection, that is not just zero, then the manifolds themselves are not locally separated x dot. Of course, the picture one usually is given in first grade, first year in the university, is something like this. So you have the parabola, and the tangent space is at zero, and you have this the abscissa. This is a straight line. The intersection of the tangent spaces to the straight line, to the parabola at zero, they coincide. This is non-trivial. This is a whole line. But nevertheless, the parabola and the straight line are locally separated at zero. So they have just one common point. And this is because the parabola and the straight line are not transversal. So if you have the parabola at zero, this straight line, they are already transversal at zero, and in this picture they are not. They are not. So I think it's okay, pretty clear for everybody. And in the absence of smoothness, one cannot rely on existence of tangent spaces. In the whole part of mathematics called non-smooth analysis, for approximations of set are used usually cones, normally closed and convex, instead of tangent spaces. And of course, when you speak about functions, some subdifferential are used instead of derivatives. So in order to proceed, it is Hector Sussman, 200 year, he speaks about transversality of cones already, not of manifolds. So if you have two convex closed cones, it is said that they are transversal if the difference is the whole space, and they are strongly transversal if the difference is the whole space and their intersection is non-trivial. And again, Sussman proves that if you have two closed sets, in a finite dimensional space in Rn. And you have approximating cones to A and to B respectively at x0. So he proves that if CA and CB are both approximate Clark tangent cones, then A and B are not locally separated at the point x0, which is exactly a non-separation result we need. He also proved that if both cones are considered in the sense of Boltiansky, again, you have the same thing. And it was a really interesting story that if one of the set is Clark tangent cone and the other one is Boltiansky tangent cone, then non-separation result, even in finite dimension, may fail. And it's an example due to Bresson. But this is in finite dimensions. If you want to push this in infinite dimensional space, then strong transversality in this sense of Clark approximating cones is not sufficient for a non-separation result. And here is the very easy counterexample, the standard Hilbert cube in L2. There is no simpler infinite dimensional space than little L2, you know. It's Hilbert, it's really fine, really nice. Never, and A is convex, B is a ray. So the sets are really nice again. Nevertheless, the Clark tangent cone to A at the origin is the whole space. And then, of course, the Clark tangent cones of A and B at the origin are strongly transversal, while the sets A and B are locally separated at the origin. So in infinite dimensional space, this Sussman's result fails. One needs better approximation, one needs new ideas. In fact, yes, there is sufficient condition for non-separating of two sets. And it's again for non-separation result of two sets. And it is connected to, again, to transversality. Transversality has been considered and generalized many and many times in different directions by different authors. And what's written here, it's year 2015. It's subtransversality. It's the weakest of this all transversality notions, and it is due to Alexander Joffe and Adrian Lewis. This is the definition. If you have two closed subsets of the Banach space X, they are said to be subtransversal at the point of their intersection if there exists a positive constant such that the distance from any point from any I'm afraid that this is not the whole definition here. From any point from a fixed neighborhood of x dot to the intersection is majorized by k times the distance to the sum of the distance to A and B, or maximum, does not matter. So this is subtransversality, very interesting notion. It has been introduced as a key assumption for linear convergence of sequences generated by projection algorithms. So from numerical analysis comes the motivation. But anyway, in fact, very similar notion has been used for proving some rule for limiting subdifferentials. And it took some time, decades, for realizing this. But from our point of view, just now, it is remarkable that subtransversality implies a rather general non-separation result, which is crucial for obtaining necessary optimality condition. As a matter of fact, we used such non-separation result for optimal control problems with infinite dimensional state space, which is a close relative to what we're doing now, but not the same, of course. So here is a non-separation result. If two closed subsets of a Banach space are subtransversal at a point of their intersection, and delta is the radius of the neighborhood, which lacked the previous slide, and k is this constant. If you can find tangent vectors to A and B, and no, I'm not going to. There are the exact definition of Boolean tangent cone and derivable tangent cone, but it's specialized, I don't think. Tangent vectors of subtime to A and to B, which are close enough, then A and B cannot be locally separated at the point x0. By the way, because this conference dedicated to women in mathematics, I would like to say that the first named author here, Mira Bivas, does not attend this conference because this summer she gave a birth of a baby girl, and now she is very busy, cannot spare time for talks or something like this, and it's important in a way. And having a non-separation result, subtransversality can help for proving an abstract Lagrange multiplier rule. So if we consider an abstract optimization problem in a Banach space X, we want to find the minimum of f subject to X belongs to S, where S is some closed subset of the Banach space and f is a lower semi-continuous and proper function on X. Then if x0 is the solution of this problem, you may approximate both the epigraph of f and the constraint. And here are written closed convex cones, which are big enough. That is, this is the Ohridski's version of approximating. So C tilde C is a closed convex cone contained in the Bulligan approximating cone to the epigraph at the point x0, f of x0, and CFS, and the other one is contained in the Bulligan tangent cone to S. And at least one of them consists of derivable tangent vectors. Then we have the following alternative. If the approximation to the epigraph minus this is the approximation to the constraint times minus infinity the value of the functional at the solution. This is the approximating cone. If this difference is not dense in x times r, then you can separate them. Then you can find a Lagrange multiplier that is non-trivial functional xi in eta in x star times r. That is xi is in the conjugate of x, eta is a number. This is non-trivial. Eta is 0 on 1, and one of the approximating cones in a negative half space, and the other one is in the positive half space with respect to this function. This is one of the alternatives, and this is the good alternative. You can find a Lagrange multiplier. The other alternative is this difference is dense. Okay, this is the bad alternative. And if it happens, then the epigraph and this set are not subtransversal at the reference point. So finding a Lagrange multiplier depends on proving that this case B is impossible. And it is the key, it is the worst of all trying to prove, because one needs to be very precise in the, this is too general. One should specify the cones, the functional and so on, in order to be able to prove that this is impossible. That is, if the cones are the difference of the cones are dense, then these sets are subtransversal. So this is impossible. So we want to prove that in some cases some sets are subtransversal. The definition of subtransversality is very nice, it's easy to understand, but to prove it is not that easy. It's not that easy. How to do it? Okay, our approach to proving tangential transversality, to proving subtransversality is proving a local condition which implies subtransversality. You called it tangential transversality. I'm pretty aware that this is not a good term, but anyway, it already exists. So here is the definition of tangential transversality, and the idea is that whenever you have two closed subsets, x dot is in their intersection, in some neighborhood of x dot, you can somehow uniformly pull together these two sets. That is, whenever in this neighborhood you have a point in one set, a point in the other set, then you can move them just a little bit. This is, you have sequence Tn tending to 0, and if you can move what, in order to stay in A, you push a bit xa to another point in A, such that here the norm of this perturbation is less than Tm times a global constant. The same with the other thing, the same with xb. You push a little bit, and this is this perturbation is measured. Its norm is measured by Tm times this global constant. Then this is the difference of the perturbed points. The norm of this difference is less than the norm of the difference of x and b minus t times Tm times eta, and eta is another global constant. So you can push them together at a linear rate. At a linear rate, you can move a little bit one of the point, the other point, such that they are closer at a linear rate. At a linear rate with respect to the perturbation. Linear with respect to the perturbation. This is very much more useful, much more easy to use when you have some information about the tangential approximations of the set. When you have some tangents, you know something about it, it's easier to move a little bit and to have such estimate instead of proving some global inequality you don't know how. And tangential transversality implies some transversality. We proved it. I'm going to skip it. I really don't think that stating the exact definitions of Clark tangent cone, which is some very uniform one, derivable tangent cone and Burikan tangent cone would be of any use now, because there is no time to understand everything. People who are used to non-smooth analysis know, and the others can look at these definitions at the slides. So the first attempt to overcome the difficulty I spoke about, that even the smallest, the best approximations of these classic cones fail in infinite dimension. A non-separation result fails. Our first attempt was to approximate even tighter set, and we introduced this notion of uniform tangent sets. So we already approximate not by a cone, but by a bounded set. And the point is that look at the definition of Clark tangent cone. For every epsilon there exists delta, such that whenever t is there and y is in delta neighborhood of the reference point, here it is y, then you have this inclusion, that is okay. In fact, the geometry is, let me try to again, oh sorry, sorry, I have problems. So let us give up the picture. I wanted to draw some cone which intersects the set itself here. you have this correction of small ball. But in any way, the point is that in this definition, whenever you have a vector belonging to the Clark tangent colony, for every epsilon, there exists delta so and so. And for uniform tangent sets, you want this delta to be one and the same for all vectors in the uniform tangent set. So, usual uniformity. And the first thing we understood that whenever you have two closed subsets of the Banach space X and a point in their intersection, if there exists uniform tangent sets to A at this point and to B at this point, and if the difference of these uniform tangent sets covers a neighborhood, is dense in a neighborhood of the origin, then A and B are tangentially transversal at x0. And as a matter of fact, it proves, it shows why this Hilbert cube with the ray cannot be separated. It somehow solves this question. But in a way, this is too strong. This assumption here is too strong. It's very good, but it gives it, as a matter of fact, implies transversality, not subtransversality. It's too strong. And for non-separation result, we need less. But I told about it because it was our first attempt, and moreover, the notion of uniform tangent set somehow is the uniformity of approximation is underlying for most of the considerations which I'm going to speak from now on. Oh dear, I'm going to skip it because the time is going fast. So here some properties of uniform tangent sets are stated. You can take the closed convex hull and so on. For a convex set which is if S is a convex set which is bounded, that just the set minus the point is a uniform tangent set. So convex sets are uniform tangent sets to themselves, roughly speaking. And now let us, so it was an excursion in order to explain transversality, subtransversality, the importance of transversality, subtransversality, but why I said that this transversality is too much. Because we wanted somehow to cover the best of known results for the basic problem of the calculus of variation. For the time being, it is belongs to Francis Clark, and you see 15 years from then, but nothing happened. So the condition imposed by Clark on the integrand, and it's connected to pseudo-Lipschitz. It's in fact pseudo-Lipschitz condition, which was stated by Aubin much earlier. It's the following, and it is pointwise. It's finite dimension. So Clark assumed that there exists for the integrand in the basic problem of the calculus of variation. He assumed that there exists a summable function, non-negative values. The summable function is called k, and a positive real epsilon, such that for almost all t in the interval, whenever you start from a point it is already in our ending point. It is in epsilon neighborhood of x bar t. X bar is the solution curve. And each point, I'm sorry, here should not be epsilon. Each point in, and each point y, whenever you have direction u with norm less than y and lambda small enough, you can find v which is less than k of t, and this differential quotient is less than k of t again. This is a mistake in the slides. I'm sorry for it, because as a matter of fact, y need not be close to y bar y at the point t. It can be as far as you wish. One needs time to understand this. So you have a small differential quotient if you fix x here should be y. If you fix x, y, and u, and then you can find v such that the differential quotient is small and v is small in the same sense. How to look at this condition? It's pointwise. We wanted to understand this condition from an infinite dimensional point of view. And we establish its relation to the original idea of perturbation and correction of the epigraph, which belongs to Bourvain and Stroivers, and it dates from long ago, from 1985. And it has been introduced by very different reasons for measuring boundary behavior of clad tangent cone. So we have a closed subset of Banach space X and some point, and in it, it is said that A is massive or compactly elliptic. Massive is a term that belongs to Alexander Yoffet. But it somehow expresses the idea of this notion. If there exists positive reals epsilon and delta and a compact set K such that for all small enough t, you have the following conclusions. So you start from a point in a neighborhood of x0 that belongs to A. You perturb it by a vector of norm less than epsilon. And you can go back to a point in A by correcting by an element from the compact set K. So you move in every direction. This is the right T here. But you can go back to A by an element of a small set. This is an infinite dimensional ball, is big, and K is compact. People used it. This is extensively this notion, and the main line for it were as a sufficient condition for sum rule for limiting subdifferentials, and it's connected to sub transversality we did it, we prove directly that if one of the sets, if you have two closed subsets, if one of the set is massive at this common point x0, and the difference of Clark tangent cone is dense, then A and B are tangentially transversal and therefore subtransversal. This is one of our main ideas. I mean, the techniques we used is different because we avoid going to the conjugate space to speak about normals. People use it almost all the time using normals. Going to the conjugate space, we keep it in the primal space, and we avoid again variational principles, because from our point of view it somehow makes the geometry of the things less transparent. And here is an infinite dimensional formulation of the Aubin condition, which we called Bourvin-Struivels condition because it looks very much like the condition of Bourvin and Struivels. So you have two Banach spaces, lower semi-continuous function which has finite values. And we say that F satisfies the Bourvin-Struivels condition with correcting set U if there exist positive reals bar delta and k such that you have this, so you are in a delta neighborhood of this reference point in the epigraph. You move a bit, but here is just the first variable, and you can go back to the epigraph by correcting by a bounded set, by this correcting set here u, and a bounded set with respect to the third variable, which is just a number, a real number. This is a direct corollary. If you have the basic problem of the calculus of variations, and you have the integral functional Aubin condition, just integrating, you obtain this, and then the correcting set is this set, all elements of L1, which pointwise are majorized by a summable function k of t. You know, okay, Mina, I know, I'll just, I know the time has gone. I got, okay, thank you. So this is, as a matter of fact, not, it's a small set. It's weakly compact in L1. Anyway, and we proved something and so on, but it is okay. It is already old, and what we did this spring is that we proved another theorem which is far away, okay, much more general for obtaining a Lagrange multiplier, and the correcting sets are bigger. So I'll just state the main result. If you have Banach spaces and a function which is lower semi-continuous, and the constraint is okay, a point plus a linear space. Here L is the integration. It's a bounded operator on L1. If you speak about the basic problem of the calculus of variations, and we defined, and we are proud of it. We don't know how to use it, but we like it very much. Cone which is bigger than the Clark tangent cone, and which is where the inaccuracy of the approximation is positive. And here the inaccuracy, you see here, this is the distance to the constraint, the distance to the constraint. So you closer to the constraint, you have to work with bigger accuracy. You farther from the constraint, you have to, you are allowed to to be loose. So if you have a variational condition like this, you have a correcting set, and here you can add up uniform tangent set to the epigraph. The condition on the correcting set is this: the measure of non-compactness of the first variable minus the value of the function of the operator L on the second variable, if this measure of non-compactness is small, and this is dense, and that is small enough, then these sets which are crucial for us, the epigraph of phi and the constraint times minus infinity, the value, are tangentially transversal at the solution, and from here we get Lagrange multiplier rule. Lagrange multiplier rule with respect to any closed convex subcone of this d et. As a matter of fact, Clark tangent cone can be used for it, but it's bigger. It's bigger. So thank you for your attention, and sorry for exceeding the time.
Thank you very much. Any questions?
How can I stop sharing?
Yes, please.
Yes, but how?
Doesn't matter, you can leave it there. If someone wants to ask a questions, we know already it's not easy, but if someone wants to ask a question, he can unmute himself.
I'm sorry, I couldn't do it. So was there a question?
I don't see one. It's not, as we said, it's not very social, the Zoom, but nevertheless, the talk was extremely interesting, and thank you so much. We see the women power in this day.
Okay, sure. Thank you very much.
Okay, so the next, it's the last session for today, and the next morning we start again at 10 a.m.
Okay, thanks.
Okay.
Okay.
Thank you.
Bye-bye.
Bye-bye.